Mm-hmm. Okay. So, can I start?
I think yes.
Okay, thank you. Okay, so today I will talk about Cohen-Jones construction. So the talk is based on a paper, homotopy theoretic realization of string topology. By Cohen and Jones. Okay, so first of all, I want to sketch an idea of what we're trying to do here. So first of all, we have the so-called Chess-Sullivan multiplication on free loops. By the way, should I turn the light on, or is it okay? Okay. Chess-Sullivan multiplication. Let M be a closed compact manifold. Then we denote by Lm the space of free smooth loops on this manifold. And so we have assumed that M has a dimension D. Then we have a degree D multiplication, or better still, degree minus D on homology of this free loop space. This multiplication endows homology of the free loop space, the structure of ring, and also there are some additional structures, but today I will only talk about the ring structure. What else? So I can briefly explain how this multiplication is constructed, at least in the original paper by Chess and Sullivan. So we can take the following composite map. So we have an evaluation map from free loops to our base manifold, which just takes the base point of a loop. So if we have a loop here, we just take and map it to its base point. And so we have the following composite map, which works like this. So we have a Q cycle here. We then, wait a second. I'm sorry. I'm sorry. So here it's not quite correct. Okay, so yeah, we have such an evaluation map here, and also we can take the following space. So we take fibered product of two copies of Lm over M, so those are loops with which have the same base point on the evaluation map. And then this thing here is co-dimension D submanifold inside of Lm times Lm. I will explain later why is it true. It's almost trivial, but the fact is that we can take the Thom space of this full back bundle over this fibered product. And we can take a cycle here and intersect it with this submanifold. And then what we do next, we just take a Thom isomorphism and we obtain a map from here to here.
Okay, so this TH EVTM
is a Thom's.
Basically the normal, it's a neighborhood of LM cross LM over M inside LM cross LM.
Yes, yes. So that's how it's supposed to work. So that's Chas-Sullivan multiplication. And our goal today will be to construct this multiplication from a certain ring spectrum, which I will introduce in just a few moments. Okay.
So this explains the first arrow. What's the second arrow?
The second arrow is the Thom isomorphism coupled with the projection from Lm times Lm over M to Lm.
Well, I think it's worthwhile to write it down.
Okay. So we have a Thom isomorphism. And then we may project it to Lm. So yeah, that explains the second arrow. Okay.
In the first arrow, you said it's intersection.
Yeah, so we have a submanifold here. We can intersect the cycle with this submanifold, and then we get this.
Well, basically, it's the following thing. We collapse the complement of a small neighborhood of Lm cross Lm over M inside Lm cross Lm over a point.
Yeah.
The result is a Thom space, and basically the first arrow is just a collapsing map.
Yeah. Okay, so that was like an introduction, and now I will just have a more concise talk from now on. Okay, so let me erase everything. Because I was just trying to explain what we're trying to do. We try to construct certain ring spectrum which will realize this multiplication. So first of all, I will recall something about spontaneous Thom construction, although I think the last talk was already covering it, but I will fix the notation because in this paper they have a slightly unconventional notation. Okay, that's great. Then I can just don't have any regrets about repeating everything and boring everyone to death. Okay. So, first of all, consider an embedding of manifolds from P to N, where P has dimension k and N has dimension N plus k. Then we have, assume that, first of all, we have a normal bundle to this embedding, which is denoted by nu E. And we have a collapse map from N to the Tom space of this bundle, which is just the normal, well, tubular neighborhood of P together with the point plus infinity, and so the map goes like this. So, yes, I started from saying that we work with closed compact manifolds. So, yeah, so let this be P. We have a tubular neighborhood here. And so we map N to this Tom space by just taking all points outside of this neighborhood and mapping them to plus infinity, and by identity on the tubular neighborhood. Okay, so it's an open tubular neighborhood. Okay, so now what we have Tom isomorphism. So I think this is quite clear because it was already explained last time. And so also we have a push forward map which goes like this. So okay, so let's consider a specific example of this push-forward map. We can.
Why is the group in the middle of HQ of PK? Shouldn't it be a Tom space?
It's a Tom space. It's our notation for the Tom space. I'm telling all this because explicitly because I have to make you remember that this notation means Tom space of a bundle. If I write a manifold to the power of certain.
So the first map is the collapse, and the
Yeah,
second map is capping.
The second map, yeah, is capping with the Tom class.
Second map is capping with the Tom class.
Yeah. Okay, so let's consider a specific example of this push-forward map. We may consider a diagonal embedding of square of M. And what we get here is an intersection product. So here I use the fact that the normal bundle to the diagonal is precisely the tangent bundle of the manifold. So this is precisely an intersection pairing. We take two cycles here and we just intersect them with each other, and this gives us this multiplication on homology.
Part of the content of this Tom isomorphism theorem is that if you do this, you get the same thing you would get by just playing around with Poincare duality.
Yeah. Yeah, I think so, yes.
Was there an orientation somewhere?
Probably. Otherwise, we don't have any isomorphism at all. Here M is orientable. Okay, so now I will just give some short information about virtual bundles over manifolds. So we will need to take Tom spaces of virtual bundles. Okay, so basically, virtual bundle over a manifold is just definition. I'm sorry. Is a formal difference psi minus zeta. So those are two vector bundles.
And by the way, what's again your last map and your definition of multiplication projection or concatenation of loops?
Yeah, that's a great question. I think the concatenation of loops. I was wrong. Thank you. Yeah.
Sorry, which one is the last?
My definition of Chess-Sullivan multiplication. It was long ago, like 10 minutes ago.
The last arrow was ln times ln over m to ln.
Yeah, it was supposed to be a loop multiplication, yes.
So ln is a group over m, and this is the multiplication.
Yes.
Group over m.
Okay, so now we want to construct a Tom space of such virtual bundle. So let the rank of zeta be k. And we can, of course, assume that zeta is just minus psi for certain vector bundle psi. Then, in order to construct a Tom space, we just embed psi into a product of n together with a sufficiently large sufficiently large real vector space. And then we define n of minus psi as the following desuspension. So we now work with Tom spectra instead of Tom spaces of the Tom space of the orthogonal bundle inside of here. Okay? Does it make sense?
How many times do you dissuspend?
So I desuspend, I think m plus k, so m plus k is the dimension of this vector space.
What is capital M?
Capital M is just, so the rank of zeta was k, and capital M is just some natural number we add in order to have an embedding.
Okay.
So that's the definition of Tom space of a virtual vector bundle.
And the rank of the virtual vector bundle
Is
is the difference. I mean, you say that.
Yeah. Yeah. Yeah.
Why doesn't it depend on the choice of psi?
On the choice of psi,
The spectrum.
well, because there's like stable equivalent and we get the same spectrum in the end.
Okay, is this clear to everyone?
I'm not sure that it is clear to me. I'm just saying some words.
Well, yes, let's see what happens if we choose another representative. Basically, nothing happens because we can always pass from one representative to any other representative by adding copies of the trivial bundle to those representatives. Well, let's take one and add some number of the trivial bundles. Then on the level of second, we have basically the same structure.
I don't understand notation. C embedded in trivial bundle of rank M or rank M plus K plus M.
No, so that's M capital. That's some large integer.
What was M?
N.
Okay.
M capital is some large positive integer.
Sorry, M with upper index is
Just-
The capital M is bad notation. We already had another capital M
Okay.
on the right.
Maybe I'll just.
R of the ring.
And also, what is it that you can that virtual bundle to?
It's not virtual. I said that this bundle is minus psi for some bona fide bundle psi.
And we just assume it is.
Yeah, but you can see that it is sufficient to do this only for virtual bundles of this kind because other bundles can be obtained by summing with such virtual bundles.
Okay.
So here everything is
So we just extend the construction of the function space
to virtual bundles. Yes, that was the idea.
Yes, but the result is a spectrum of the space.
Okay.
And I can have them make it a common value or something.
Yes, sure. Because we just suspend so many times that. Okay. So if M is orientable, then we also have a Thom isomorphism.
Sorry, how many times did you suspend?
It's
K plus
it's K plus R, yes. As many times as the dimension of the space. So it in particular shows that if we choose another dimension of a space, nothing changes. Okay, so we also have a Thom isomorphism here.
So what is this notation for C code?
Oh, so that's an orthogonal complement of psi inside of here. So we
Thought
have,
of as a trivial bundle
yes,
with
a metric.
standard metric on that.
Yes. But the choice of the metric, once again, does not change anything up to homotopy.
I see, and the purpose so that this is the minus.
Yes. That's the idea, to realize the minus as just a complement to a trivial bundle. Okay. Okay.
Okay, does everyone understand where this thing comes from?
This thing.
Yeah.
Well, once again, I'm not proven.
What?
Does everyone understand where the arrow comes from?
suspend and after everything is done, this suspend.
Yes, it's the same thing as we saw last time for spaces, but this time for spectrum.
Yeah.
Does everyone understand why this works for spectra, at least in this particular case? Never mind the general.
Remind us what this is.
Okay. So in general, we have a cap product with Thom class, which shifts the dimension in homology. So If we just have vector bundles, then it works like this. So in order to get it here, we just need to perform this construction for this thing here. So we have an isomorphism minus k plus k like this. Then after applying the suspension, we have an isomorphism like this, I think. So is it satisfactory?
Well, does everyone understand and agree with what it says on the blackboard? If not, please let Risha know.
Yeah, because I think that this part is, oh, no, I don't agree with it either. Because the dimension here should be
If you want to explain
r minus k.
the Tom isomorphism for negative Tom space, then you should apply it to m psi what?
M psi perp, yes, that's
I see on the second line.
no, I mean, so we first applied Tom isomorphism for regular Tom spaces for psi perp, and then we desuspended.
Yeah, right. And what the second line on the left?
This one.
Yeah. Right. Yes.
Yeah, so I just wrote it like a Tom isomorphism for just regular bundles. I was just saying that we have it.
Oh, you mean side one?
Yeah.
And by homology spectrum, you mean the mass of Heidelberg mapping to spectrum, Heidelberg mapping spectrum to.
Yeah, that's one way to look at it, or we can just think of it as like shifted homology groups of spaces in spectrum.
Yes, basically in the same way as we define the homology groups, there's a fancy way and a straightforward way of which was to take the character of homology groups of the individual spaces which constitute spectrum with some shifts which come from suspension.
You said smash with HZ and then take the homology groups.
Yeah,
Yes.
that's the fancy way.
That's the fancy way.
Okay. So now we can consider Pontryagin Tom construction in another important case. For bundles over the ambient manifold. So what we do here, if we have a bundle zeta over n, then we have a map from the Tom space of this bundle to the following Tom space. So okay, so how does it work? First of all, we have a Tom space here, which is just this, or just zeta if we consider open disks, so everything works. And then we map it to the tubular neighborhood of E star of zeta together with infinity. And so this thing here gives us precisely the normal bundle plus the pullback of the bundle to the manifold P. So it looks like this. We have this bundle zeta. We have the part which is over P, and we have the normal direction. So they add up and give us the Thom space of this sum of two vector bundles over P.
Excuse me, what is E? What is
E is an embedding. So we have an embedding. So we pull back this bundle zeta to P, and we have, so that's like the, so to speak, tangent direction. And we have a normal direction of this bundle. And when we collapse everything, we just get a map from here to here. Is it clear? Okay.
So does everyone agree with what Grisha has just explained?
Sorry, what?
By D of data, you mean the
Disks, open disks.
does that depend on metric or?
Well, we can choose a metric and then it doesn't matter. Okay. So this construction works also for virtual vector bundles. Okay, but, well, I think that you can believe me that it works for virtual vector bundles, or I can just write down the formulas.
Well, let's see. Do we believe Grisha?
If not, I can write it down. It's not hard. We just need to, once again, embed into this large vector space, then take the perpendicular bundle. I can, okay. So, first of all, note that I can decompose this. I think the main problem here is that I don't believe myself. So we can decompose this Thom space into the smash product. And then what we get when we try to do it for virtual vector bundles, we have a map that looks like this. Yes?
What do you want to say?
I want to say how it works for...
First line, I mean, this is
the first...
relative smash or something like this.
No, it's just regular smash.
Well, the Thom space of a direct sum is not the same as the smash of the Thom space.
Yeah.
So you need to take fiberwise smash.
Yeah, okay.
Knowledge, but what you need?
I was just explaining how we should do it for virtual vector bundles. So first of all, to do it for virtual vector bundles, we note that we can do it for just regular vector bundles like this. And then we do this construction for psi perp. And then what do we do next? Well, we just desuspend everything here. So, and we get a map of Thom spectra. And so the point was that we can desuspend it. So since we have a smash product, the suspension can be applied to just one factor instead of the whole thing. So it's the same as desuspending just this guy here and leaving a normal bundle B. And so this shows that the construction works for virtual vector bundles because we have the desuspension of this perpendicular thing here. So yeah, that explains why this construction works both for regular vector bundles and virtual ones. Okay, so now I'm ready to give a construction of this spectrum which will give us just Sullivan multiplication. If it's okay, I will erase this board. Okay? Are there any questions?
I don't think I understand what you mean by relative smash product. These phone spaces at P to some power, they're not spaces over P, are they?
No, no.
So what do we mean by this wedge with a dot on it?
You can take the fiber product of open disk and then add infinity point.
Yeah. But I have to confess, I think in the paper they just write smash product. This is strange, but let me just check it real quick. Okay, so okay. No, they just say that we can do this. No. So that was I think something that I came up with, and it is obviously wrong. So if you know how to correct it, please say it now.
To correct what?
The fact that I just took some operation that doesn't exist.
Let's see what we mean. Do we really need to the first line? We want to construct the construction of a virtual vector bundle.
Yes. So
Basically, we haven't you already defined the time spectrum?
yes, we did.
What did we do? We took an orthogonal complement and then took the time
Oh yeah, right.
of the complement and then shifted the result.
Okay, so yeah, you're absolutely right. So we just can do it like this, and everything works, right?
Okay, so the first line wasn't necessary. It was sort of trivial, but then it's not necessary.
Yeah, okay.
Does the second line make any sense?
Yeah, sure, but what's the statement about negative tone spaces? Because it seems that they depend on the dimension of n and p, so the map is not between corresponding negative tones.
Why they depend on dimension of n and p?
Because you define like this, you shift.
No, k is the rank of vector bundle. It is not related to dimensions of manifolds.
Sorry. Okay. Okay.
Okay, that's great. So now let me do the construction of the spectrum. So first, what do? We have a diagonal embedding from M to M square. And we have a virtual vector bundle. So this is a vector bundle over the square. So we get a map of spectra, which looks like this.
Could you please recall what the blocks product?
Just direct product over two factors. So
Not,
no, maybe that's the wrong notation. I should write it.
block sum. You pull back and then sum? What is the rank?
The rank is like
Does it add
Two
or does it
times.
multiply?
no, two times.
Then box sum.
Box sum.
Okay, yeah, thank you. Okay, so
Is this the same presentation Kevin and James used in the paper?
no, I don't think so.
This is the rank notation.
Okay,
It's not my fault Conan and Jones don't know what a tensor product is.
yeah. Okay, so we have the following thing. So this is the normal bundle to delta, and we add the pullback of this virtual bundle to this manifold, and we get this thing here. Okay.
Does everyone understand where this arrow comes from?
It's an example of the thing we just last did, right?
Yes, yes, exactly. But does everyone agree with this?
I agree. I agree that the normal bundle of M and N cross M is given.
So basically, we do what we just did, namely we make the font space of vector bundle of a large manifold, and then map it to the font space of the restriction plus the normal bundle.
Okay, so the pullback of this bundle is minus 2tm. And after simplifying this thing here, we just get m to the power of minus tm. And that suggests the construction. So
Okay, so what does this mean? Are we allowed to add and subtract virtual vector bundles? Well, yes, but the thing is, this plastic quality is again the spectrum of the space.
yes. Okay, so now we have the following thing. We have this sort of multiplication. And now I will just make this.
You're going to tell us what this is.
That's what it says on
Yeah.
on the board.
You're saying the left-hand side is this smash product.
Yeah, I think so.
Yes, because this time it's the direct direct product of
Yeah.
two bundles. By the way, does everyone? Well, we all understand what the direct the Cartesian product of two genuine vector bundles is. But what about virtual vector bundles? Does everyone understand how we take the direct product? If not, well, would we
the only way this is not obvious is because one gives the wrong definition of a virtual vector bundle. So if you give the right definition as the group completion, and you take like formal linear combinations modulo the appropriate relations, then well, they are formal linear combinations, so you know what this one is.
Yeah, but this is not what we did. We said a virtual bundle is a class of stable equivalents of German bundles.
But I mean, this is equivalent because you're in this blocking situation to taking over a degree.
Yes, yes, it's equivalent. Does everyone agree that there is a direct product for virtual vector bundles, and moreover, the Tom space of the direct product is the wedge of the Tom spaces, meaning the Tom spectrum is the wedge of is the smash of the Tom spectrum. For spaces, for Tom spaces, this is straightforward. What about Tom spectrum? Shall we just say we believe it, or shall we check? Well, let's see. Do you believe this?
Sometimes. This time I believe myself. Yes, yes, I do.
Well, can you briefly explain at least how this is relatively straightforward.
Okay.
Let's nonetheless let's do this.
Okay, sure. So if we have some, thank you. Yes. Okay, so this is supposed to be d of x times, d of zeta times d of psi, and mod out by the product. No, this is wrong, sorry. Mod out by the product. Okay, so now we just see that this is precisely what the smash product is, because we just took direct product and then we just collapsed the bouquet of two.
Yes. For spaces, this is straightforward.
Okay. Well, for spectra, it is, I think, also straightforward from the description for spaces, no?
Yes, let's try to do this explicitly if possible.
What do you mean by this spectrum? Do you mean suspension spectrum?
Well, we did define the tone spectrum of the negative of a bundle, and then we claim that the same is true for if I replace psi and the other one psi and zeta by the negative of the spectrum.
Okay, so first of all we get x minus zeta perpendicular smash y minus psi perpendicular, and then we should desuspend it minus, so R plus K zeta plus K psi times. Since smash product commutes with suspension, we get the suspension minus, well, since we can assume that R is arbitrarily large, yes, we can think that it is 2R instead of just R. And we get what we wanted. So, sorry. So that shows it for spectra, I think.
Okay, does this make any sense?
Great. So now, now I want to describe the multiplication.
And by the way, where else? We have constructed this map from m cross n to the blah 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 to m to the minus tm.
Mm-hmm. Okay, so but that is not yet our spectrum. So let me now write down what is our spectrum. So can I erase this computation?
Unless there are people who rather have it. By the way, we will need to have a break soon.
I think I should define the spectrum and then we can have a break. Okay, so as I told earlier, we have an evaluation map from Lm to M. Then we can just take the pullback of Tm under this evaluation map. And then we can take Tom space of Lm under this evaluation map, and we will denote it like this. And so this thing here is the desired ring spectrum.
Do you have that embedding?
Uh, Minus Tm is, well, minus Tm is minus Tm over M.
Have an embedding. Did you embed m in something?
Why would I?
TM is just a bundle on them.
Yes.
Because if you're using minus tm, you should have some computation of tm.
No. We just used this embedding to give a construction of Tom space, but we don't need this embedding.
More explicitly, we have this tm, which is the virtual bundle. We add something and get the trivial bundle, take the orthogonal bundle. Then we pull back under EB. We get the German bundle take the top space, and then this is there.
Okay, so I think that we can make a break here. So I will show that multiplication on this ring spectrum actually induces multiplication defined by Chess and Sullivan in the second part of the talk.
Chris, if you need to explain, then we'll be able to handle the rest in a second.
As you wish.
Well,
If we can take a short break, then I can attend more of the talk.
okay, let's cancel this short. Okay, let's have a break until 6.
Нам уже очевидно, что это там не надо...
Нет. Там пока вообще ничего не очевидно.
Сейчас говоришь, что не очевидно.
Что есть умножение вот в этом спектре, как я написал.
Да, я согласен.
Но мы его скоро обнаружим.
Это в какой статье все происходит? Это Горинов Джонс, да?
Да-да. Homotopy theoretic realization of string topology.
Так, есть у нас какие-то еще вопросы к рису, которые мы хотели задать, пока рис побежал? Только рис убежит, а потом не будет отвечать на письма.
Ну он будет отвечать, почему? Мне же он ответил. Такой вопрос, что там написано в этом ответе?
Нет, ну просто отвечать на письма, так сказать, доставка. Вот, я ответил на письмо, в смысле, две периодически.
Chris, did you receive an email from Latin regarding commercial paper?
I received some kind of automated email where I click and say, yes, I'll do the job. And I did click and say, yes, I'll do the job.
When did you get that email?
Sometime this week, I think.
Okay. Did you look at the paper at all?
A little bit.
What I think?
I'm sure it's fine. I mean, I've talked to them about all of this in depth before, but I mean, I should, to do an honest job, really read it through it line by line, but
Okay, well, I don't think there are serious mistakes. But,
no. And I would be surprised if there are even minor mistakes. I mean,
Well, I did look at it, but serious mistakes.
there could be some typos, of course, but
Well, I don't think there are too many, but there's always possible.
okay, well, I will get that read through this week. But you know, I've been talking to them about this project for a long time, and they know what they're doing.
Well, it's always worthwhile to check just in
Yeah.
case. Thank you. Okay, maybe well, we have 4 more minutes, but do we really need them? So maybe we could just begin.
Okay. So I explained how to get this ring spectrum. Now I will explain how to construct the ring structure on it. So we still need a multiplication. And to find such multiplication, we will consider the following diagram. So it is a Cartesian diagram. So what's happening here? Well, we just take the pullback of Lm times Lm along this diagonal map, and we get Lm times Lm over M. So, yeah. In particular, it exhibits Lm times Lm over M as a dimension, codimension D submanifold inside of Lm times Lm, because M is a codimension D submanifold inside of M times M. And so, yeah. And so we also know how to get a normal bundle of this embedding, because we just need to pull back the normal bundle of delta, which is just a tangent bundle, along the map of evaluation.
I mean, what really is this like?
What
do we need to know about this? I mean, in what sense is it a codimension D embedding? It's that you have a kind of...
not normal, we have a tubular neighborhood
We have a tubular neighborhood
of dimension.
by this normal bundle.
Yeah.
Given by some ring D bundle.
Yeah. Okay, so we have a map gamma from Lm times M times Lm over M to Lm, which takes two loops and just multiplies them. Of course, we need the smoothing and reparametrization in order to get a smooth loop, but it's a standard technique how to get from non-smooth loop a smooth loop in this case. We just multiply it by some disgusting function which has all derivatives equal to 0 at 0, and we get the reparametrization. Okay. So yeah, as I was saying, we have this map delta tilde.
The way we do this, LM is continuous maps, not smooth maps.
No, there are smooth loops.
There's smooth loops. Okay.
I don't think this should matter so very much.
No, it
I
shouldn't.
think that in all the papers they take it to be partially smooth, so
I also think it shouldn't matter.
It shouldn't matter, yes. Okay, so we have a tubular neighborhood of delta tilde, which is just the inverse image of this thing, which is equal to inverse image of Tm. Okay, so we have a Pontryagin-Thom map.
I can't see.
Yes, we have a Pontryagin-Thom map, which is induced by this normal bundle. So we have a. Well, let me write it down, and you'll immediately understand what I mean. So it's Pontryagin-Thom collapse map. We collapse everything outside of the tubular neighborhood to infinity, and we get this thing. Yeah, and so we will denote this last thing simply by where? Tm, yes. This is the Thom space of.
But the last bit is just notation.
Yes, yeah.
Let's stop writing evaluation because it's annoying.
Yeah. So we have another commutative diagram. Let me first write it, then I'll show it to you. So this is just by naturality of pentagon Tom construction. We have this collapse map here, and we have the same collapse map here. And so everything works. Okay. So one may view this map induced by tau on homology as intersection product.
Sorry, I lost it for a second. Okay.
Yes. That says a lot about the quality of my talk. Okay, so we have an intersection product which looks like this. Okay. Okay, so this corresponds to taking a cycle. Well, wait a second.
Okay, so the first arrow is just tau levels up, isn't it?
Yes. So the first one is tau star, but also yeah, but also it is. Wait a second.
Yeah, you can vary this arrow into
Yeah.
first is lm times lm over m, and then concatenation, right?
Yes. But wait a second. Let me check, because I think that I made a mistake. I'm not reading from the original paper. I'm reading from my notes, and I think that I made some stupid mistake here, because this minus d is supposed to come from Thom isomorphism, but
Looks like it works.
yeah. So I was obviously wrong here. Yeah, so it should look like this.
Yes, but then there was a map from this thing into LM just a single column.
To LM, yes, of course.
Which is
Um,
composite.
Yeah. So gamma is a loop composite. Yes. So we get the following diagram, and that basically explains how the multiplication is constructed. So we just need to take the composition of loop concatenation and this Pantelian-Thom map. Okay. So another interpretation is that we take a cycle here, we intersect it with this submanifold which has codimension d inside of this product. So that's another interpretation of this arrow here.
Okay, does everyone understand what has just happened? If not, please select vision.
This Thom collapse, Thom isomorphism, loop multiplication.
Yeah. Okay. So that was an interpretation of this map in terms of intersections, and also I added this loop concatenation homomorphism, and we essentially got a multiplication in homology.
And by the way, did we review this multiplication in any examples or not? In the first week?
Well, supposedly we did up to mistakes. Well, no, not exactly.
No,
We
there
did
was a bracket.
we did the bracket which is extracted from this, so no, we did not.
Yes, but do we know how to get how this thing is related to the bracket?
Eventually.
We
So you need to introduce the circle action in order, and then take some equivariant homology to get the bracket.
Okay, so this is supposed to be related to the bracket, but we don't know it yet.
We don't know it yet, so this is just some other operation.
Okay.
It's it's somehow directly related. I thought that bracket and the multiplication just respecting each other two different structures.
No, they exist on different spaces. So the bracket is on the equivariant homology, not other homology.
It exists already.
It's a different bracket, not the one we were talking about.
Oh.
So this also has a bracket because of this E thing, but that's a different bracket.
Yeah, I thought in one of the suggested papers for it, there was example for Riemann surfaces, and their degree of bracket was exactly so that you obtain the algebra structure on components of just ordinary loops like we did in the first seminar.
This one will have a shift. The bracket here will have a shift by 1 and minus 1, or the one we were talking about on the first handout. So they're really different.
I thought she will be d minus 2.
This will be a shift by 1 minus d, and the other one is a shift by 2 minus d, the one that we talked about before.
Okay, so
And that difference comes from the dimension of the circle.
okay, so we have an embedding of infinite dimensional manifolds. Of dimension d, and this allows us to get the following map of Thom spectra. So this is the ambient manifold. We take a pullback along to the second order product of evaluation maps of the bundle minus Tm times, or better, direct sum of two bundles minus Tm. And we go to the same thing, but over the smaller manifold. So we should have a normal bundle to this embedding, which is just the pullback of the tangent bundle, plus the pullback of this guy right here. Okay, does it make sense?
Well, we use the same construction we used already.
Yes.
Today. Basically, the normal bundle is have upper star Tm, and then we need to check the second sum is the same as the pullback of the bundle on the left under the map under the inclusion of the final product of the RAM into the direct product.
This follows from the diagram that I conveniently just erased. So we have.
Yes, but does everyone agree? We elements. We have the one on the right and the one on the left. And we want to check that one is the pullback of the other under the inclusion. Do we want to check it, or does everyone believe?
It looks a little funny,
Okay.
because on the right-hand side there, something must cancel or something.
Yeah,
There's
yeah.
a different number of summons.
Yeah, we will cancel it in just a moment.
Okay.
So, as you said, something should cancel something. So this thing right here is in fact equal to minus 2tm. And this minus 2 cancels with this thing here. So what we get here is actually a map of Thom spectra, which looks like this. So we have Lm minus Tm smash Lm minus Tm. I just rewrote the left-hand side. And then it goes to Lm times m times Lm over m minus Tm. So that's our notation. We agreed to drop this evaluation's upper star. So we have this map of Thom spectra. And now we can define a multiplication on this guy here by doing this composite. So So gamma is once again a loop concatenation, and we get the map of the multiplication on the spectrum Lm to the power minus Tm. Is it clear?
Hold on. So what's the last error on the level spectrum? Yes.
Yeah, that's just so we can take first of all the map of spaces Lm times Lm over m to Lm, given by concatenation of loops.
Yes.
And then since the functor of Thom spectrum is covariant, we just get a map
Okay, so
on spectra.
Because
Okay.
because that concatenation map is a map over M, the one bundle pulls back to the other.
Yes. Yes.
And that's an important point, I suppose.
Yes. It is.
And what does this have to do with the loop multiplication that you defined? Are you going to tell us that?
So this is precisely the Thom space functor applied to loop multiplication.
So how? I mean, where does homology Ln cross Ln appear?
Sorry, I didn't understand.
Well, up here on the top line,
Yeah.
this kind of stuff involving a Thom spectrum only appears in the middle term, but the source and target are pure Lm things. How are they going to appear out of? What is the relation between, I don't know, homology of Lm to the power minus Tm and
But by Thom isomorphism.
okay.
So everything is just shifted by some constant.
So how does it work out in terms of the shifts? Show us.
If we have Lm, so I think we should plus 2d should be equal to I'm not sure that I'm writing it correctly here, but I think it should be something like that.
Sorry, what's the claim? Isn't it supposed to be a plus instead of minus, right?
Here?
Plus D, yeah.
No, plus D.
Yeah, plus D would be fine, because then when you subtract minus 2D from both, you would get.
Yeah, I think. Yeah, I think so. Yeah, okay, so I didn't really want to draw this diagram, so it just somehow happened, but
Well, the second helps.
okay. It's great.
Basically, what happened is we have this product map, and we identified the source and the target with the homology of subspectrum, and we have we said that this map is induced by some map of spectra. So we have a multiplication on the level of spectra, which is shown on the left, meaning we have Lm to the minus Tm, which is the spectrum. On top of that is a regular.
Okay, yes.
By the way, is it associative, commutative, neither?
Yeah, it is both associative and I'm not sure about being commutative, but it is associative. I will show it just in a small moment.
I don't think it should be commutative. It should be at most E2.
Well,
So it will be commutative at the homology level, but not at the level of spectra.
yeah, I'm sure you're right, because multiplication on the loops is not necessarily commutative. So it is somehow coherent with the multiplication on based loops. So no, it should not be commutative. Okay. So some properties of this multiplication. First of all, let's think that Lm consists of more loops, meaning that we consider not loops of length 1, but loops of arbitrary length. So we have a strictly associative multiplication on Lm, or on omega m, or on Lm if we consider Lm as a groupoid or something like that. Then, since Pantelian-Thom construction is natural, mu is also strictly associative. Okay, yeah, so that should be right. So also I want to show that the Thom spectrum Lm to the power minus Tm is unital. To do this, I just observe that we have unit on the spectrum m to the power minus Tm. So is unital. And we have a section sigma from M to Lm, which just maps points of M to constant loops on M.
Do you mean Lm
Lm,
to
yes.
the minus 2m? You wrote m to the minus tm
No, M to the minus Tm is unital
as what?
as a spectrum.
What does unital mean? It just says a point.
Yes.
Because you define the multiplication on an m to the minus tm.
We obviously define the multiplication on M minus Tm by Pantelian-Thom map. Recall that we had this thing, which then mapped to M to the power Tm plus delta upper star of Tm box plus minus Tm. And then we just did this and we got a multiplication on M to the power minus Tm. So one of the points I will show is that actually the map of evaluation is a homomorphism of ring spectra. So we have a multiplication and we also have a section which induces the unit on Lm to the power minus Tm after applying the functor minus Tm.
So basically, is it true that M to the minus Tm splits off as a summand of Lm to the minus Tm?
Yeah, I think so. Since we have a section, I think this is true, yes. What sigma does?
What G does?
Sigma.
Sigma.
Sigma, what does it do?
So we have a point here, and we map it to the constant loop here. Okay.
Can you comment on commutativity on homology level? So what is statement?
I can't. I don't know. Well, I don't know why it should be commutative.
Yeah, I agree with you, but from all these papers, it seems that it should be commutative.
I don't know why from this point of view. I don't know why it should be from this point of view.
But it's true.
There is a statement that if you take in free loops the concatenation, then the concatenation of one loop and then another, and like in reverse order, they're homogeneous.
No.
I mean, if we do
if we-
base loops, just free loops.
It doesn't seem plausible.
I can look at it. Probably I'm deleting
I'm not sure. Just I don't know, if we take a wedge of two circles, then why should we get a commutative
Because
multiplication?
If you take a wedge, if you take multiplication in the fundamental group, then we take multiplication as base loops.
Yes, I understand.
Yeah, so if you take
But
the
this
free
is kind
loops,
of,
then we can just
this map is kind of relatively based, right? It's a map over M. So on the fibers, it's not commutative.
yeah.
But maybe we can somehow shift the base point so that.
Yes, we can shoot it along one of the loops and then.
Oh, okay, I see. Yeah,
Yeah.
yeah.
I don't understand how it works in lecture to solve it.
I can try to draw it, maybe. So.
But also I think when we change base point, we conjugate by some element of the fundamental group, and we can just get a commutator this way, I think. But that's besides the point of our work right now. So let me erase this and write a diagram in homology. Okay, so in homology, in the orient.
It will
By the way, if non-based loop contractible, then some conjugate to such loop is based contractible, but in free group it's nonsense, right?
So I don't know, but we don't need to know
Yeah.
that this loop concatenation is homotopy commutative. The claim is rather going to be that this kind of wrong way map followed by that will be homotopy commutative. And this, one explanation for this will be this multiplication will be realized by the action of this calculus operator. And there is two ways to multiply on a homotopy commutative. There are two orders with this homotopy.
So I will once again draw this helpful diagram that we drew now intentionally. Okay, so here we get this is Chern-Sullivan multiplication, and this way is just what we discussed earlier. So here we have a Thom isomorphism, and here we have this multiplication, which is induced from multiplication of spectra.
This is about compatibility with the two descriptors.
Yeah.
So it's funny, you basically say that if at the level of homology we have description through action of Cartier apparat, but on the level which comes from the level of morphisms to correspondences, and their concatenation would be commutative or homotopy. I don't know what is gammatic category of correspondences.
Well, I mean, the point is there'll be like maybe there'll be a whole space of correspondences and a path in that space of them. It's like a family of correspondences parameterized by some space.
But nevertheless, it seems to commutativity will hold for any oriented homology theory with respect to a tangent space of Q manifold. But there are no reason why this spectra should be even be gammatically commutative, right?
Okay.
They don't comment on this?
No, I mean,
My guess?
maybe they comment on it.
My guess would be something like,
Okay, meanwhile I can explain that we have a map of ring spectra. So So since Penrodian-Thom construction is natural, and we obtain this mu by pulling back tau, we actually get a commutative diagram like this, which shows that multiplication in Lm is compatible with multiplication in m to the power minus Tm.
Okay, and is this action also compatible with multiplication?
With multiplication of loops?
What action?
Well, yes.
Not the action, this action from m to Ln.
Oh, the section.
The constant section.
Let me think about it in just a moment.
What is the product of constant numbers? Constant.
I don't understand why it should be actually. So maybe it will help if we recall how we constructed mu. So we constructed mu by mapping to the power minus Tm. So it was given by Penrodian-Thom collapse map. And we have to think where this constant loops will go under this collapse map. I want to say that they go to infinity, but I'm not sure. Well, they either coincide or they go to infinity. And if they coincide, then yeah, I think you're right that it is compatible, because here we should have like product of sections to which, after applying this, since the value on 2 points is the same, we get just so we have a pair of constant loops, which are just the two copies of the same loop. And when we multiply them, we get once again a copy of the same loop in here.
I don't understand. What if I have a pair of points which are distinct?
They can't be distinct because this is the same map. No?
No, I have a point X on one copy of them and a point Y on the other copy of them, and they go to...
Then they should go to infinity. And then it is... okay. So certainly if we consider a map from m to the power minus m. So I think that the diagram like this should be commutative, right? This is what I was saying. So if we have, do we even have this arrow?
Yeah, it looks more like a coproduct, or what is it?
Okay. So
Let's not worry about it for the moment.
yeah. So let's leave it for now. So now we understood that we got a homomorphism of ring spectra, which is this evaluation map. And now I want to describe the relationship of this multiplication with multiplication on based loops. So let me draw another square. Consider a base point x0 inside of M, and we have a pullback. And we have a codimension D embedding of omega x0m into Lm. And so, since we're pulling back over a point, we know how the normal bundle of this embedding looks like. So we have, let's denote it by J. Then U of J is just a direct product of loops to a trivial bundle. Let's denote it like this. To a trivial bundle of dimension D. Yes. So
It's just the tangent space of that one.
yeah. And so the whole thing is like the trivial bundle over omega m. So now we can apply the Pentradian-Thom construction to this situation. Let me erase this diagram. Since we have a trivial bundle, we will now get a suspension. So Pentradian-Thom map goes like this. So M plus is M with a disjoint base point. So we have a homomorphism in homology. So this plus disappeared because we applied suspension isomorphism, and we got here what we got. So the geometric meaning of this thing here is that we take a full cycle in Lm and intersect it with omega m. So omega m is codimension D submanifold inside of Lm, and we get this intersection map. Okay.
What do you do with this?
I just did.
Probably what Rich is about to say that we have a map of rings from the homology of Lm to the Pontryagin ring of omega m.
Yes, kind of, yes. So, but not right now. So now I want to play around a little bit more with Pentradian-Thom map.
I don't think that will be true.
No, I'm also not sure because Pentradian ring has no it has different degree of.
No, it's exactly. So
No, but I don't think it should be enough. This would
I'm sure that this is not.
But how is it possible? They have different degree of multiplication.
No, your map is degree T.
Tau also shifts the degree.
Okay.
And you have concatenation on what side.
Yeah, okay. Maybe that's true.
Alexander. So this is the current.
Okay, so we have the following Pendragon Tom map. So this is a trivial bundle. So this is the normal bundle, which is trivial. This is the pullback of Tm. And since we have a commutative square like this, it is easier to see that pullback along evaluation in J is the same as pulling back over a point. So what we get, in fact, is a trivial bundle. So what we actually get here is the following thing. So since it was minus Tm, this is a trivial bundle of rank minus D. Note that this is very convenient because here we have a trivial bundle of rank D, and here we have a trivial bundle of rank minus D. So they cancel each other out, and what we get here is actually the suspension spectrum of omega m plus. Okay, so we have this composite map ρ, which we should be able to show that it is a multiplicative map. So we consider the following diagram of ring spectra. Just a moment. Let me erase something. I think this is irrelevant now. Okay, so the diagram of ring spectra looks like this. We have omega m times omega m to Lm times Lm over m. This is obviously an inclusion. And so this is a diagram of pullback squares. So here we have an evaluation map. Here we have delta. Okay, so we get a composition of Pendragon Tom maps, which looks like this. Okay, is it clear? So this is basically just constructing a Pendragon Tom map from this inclusion here. And
Okay, so the first
Yeah.
is the gradient Tom, and the second is
is also Pancadian Tom.
yes, but where did the bundle go?
It's by this construction, so we canceled. So we have a cancellation of bundles. We have a trivial bundle of rank D and a trivial bundle of rank minus D. They cancel each other out, and we get the suspension spectra here.
Okay, does everyone agree?
I don't understand tau
This?
yes, I don't understand
So if we have two complementary bundles, then we, after cancellation and taking the Tom space, we get a Tom spectrum, we get a suspension spectrum of what is there. So that's just the composite of this map and this equivalence.
yes, I don't understand what written yes.
This? Okay, so once again, this is, okay, let me repeat. So we have this inclusion, right? Okay, we can take a bundle minus Tm over Lm. So the normal bundle is trivial. The normal bundle is trivial because we're pulling back over a point. Normal bundle of this thing here is a pullback over a point. Okay, so it's trivial. But also we have this pullback of minus Tm over EF star over J star. Because minus Tm here was obtained from minus Tm over M by pulling back along evaluation star.
Okay, you mean all bundles?
Yes, yes, but this is a virtual bundle of rank minus D. And this is a virtual bundle of rank D, and they're complementary, so they annihilate, and we get a suspension spectrum.
I don't understand which non-trivial things annihilate each other. Everything is trivial, or
Yes, but yes, everything is trivial. You can think of it that way.
yeah, okay, but I still have a rather psychological problem. I don't understand what a rho is.
You mean?
What is good?
That's a great question. I mean, you want some explicit construction in terms of cycles.
Maybe, or maybe. So I mean, it seems that there is. Can you put instead of Tm anything? What the proof of claim is?
No, we can't put anything instead of Tm because.
Okay, what non-trivial appears above omega m if you replace Tm by something else?
Nothing, but we have to. Oh, okay. So the normal. So the normal bundle is always trivial. Well, okay. So this thing shouldn't be always trivial because it is not true that in general we can.
Okay, can you just write this in a readable way?
Okay. Better still. it is not equal in general to the pullback along this map, say iota, say p, along
What do you mean? The diagram commutes?
Yes, but we will not have a map from. Okay, so if we think that here we have a pullback from over bundle from.
So maybe you're right. You can do this for any bundle.
Yeah, but then what's the? Oh, okay. Yeah, so for any bundle, we will have a map to the suspension spectrum of loops. Why should that be a problem?
No, it's not a problem. Okay, I understand this one.
Okay. I'm sorry for not understanding it myself, but okay.
Shouldn't you change, shift the spectrum by the rank of
Should we shift the spectrum by? Why? We can cancel out.
are they canceling each other?
Yes, they cancel each other. Okay, so we have this diagram of two pullback squares. We have a map ρ of spectra that looks like this. And now what we get, yeah. So this is not ρ, this is ρ wedge ρ. So this is just by neutrality of Pantelian-Thom construction. So we get ρ wedge ρ when we apply smash product everywhere.
Sorry, one.
Yes.
Put everything instead of minus Tm, so we can define the same map for everything.
For any bundle, yes. That was the point of Sasha's question. Yes. Okay, so in the end, what do we get? We get another commutative diagram. Okay, so the top row is just like this. Maybe it's better if I just draw it here. So we have a concatenation of loops here. And we have a map induced by, yeah, I think that you were right, so this map is induced by multiplication of based loops. And the top map is just ρ wedge ρ. And this map is concatenation of loops, of free loops with the same base point. Okay, so this map is just ρ. So the above diagram shows that, in fact, we have the following diagram of ring spectra.
Well, this means that the lower star is a map of rings.
Yes, I said that you were right, yes. So we have a map from this Chas-Sullivan multiplication to Pantelian ring. Yes, you're absolutely right. Okay, so yeah, we have this commutative diagram. And so I will end with the formulation of the Cohen-Jones theorem, which summarizes all those properties. So first of all, we have a homomorphism of ring spectra, which is given by the evaluation map. Second, if M is orientable, then Chas-Sullivan multiplication is the same as Lm to the power minus Tm, which Lm to the power of minus Tm, to Lm to the power minus Tm. And finally, we have a homomorphism of ring spectra, rho minus Tm to the suspension spectra of loops. Which induces in homology the map from Chas-Sullivan ring to Pantelian ring of this manifold.
Okay. Well, we basically proved this theorem.
Yes. So the whole thing above was like a long proof of this theorem.
Okay. Well, are there any questions? Any questions to the speaker?
So M M minus Tm splits from Lm.
Well,
We didn't understand it.
yes. Well, that's it's not it's so clear. There is a map in one direction, but not necessarily in the other direction. And
Okay, then we have
well,
configuration of ring spectra.
there is a map of spectra in the opposite direction, but we're not sure whether or not it.
Okay, at least we have a configuration of ring spectra.
I'm not sure that it is compatible with. I mean, it is a configuration of spectra. I'm not sure that it is a configuration of ring spectra.
Yes, well, so we have a map of ring spectra in one direction, and there is a lift on the level of spectra, but we're not sure if it's compatible with multiplication.
Yes.
I mean, okay, put it that way. Is it true that Lm minus Tm as spectrum, not ring spectrum, splits as N
Yes.
minus Tm and
Yes.
suspension spectrum form?
m minus Tm in suspension spectrum of omega. I'm not so sure why would it be. Why it is the whole Lm minus Tm?
Well, these two arrows in item 1 and item 3 it's not clear how they are related, and in particular it's not clear that the
No. I take in place of evaluation just pattern of constant loops M to L1.
Yes, but it is not clear what is map of.
So what Sasha is saying that the m to the minus Tm is the kernel of sorts of the map in item 3.
Yes,
Sasha, is this what you're saying?
Yes, that's my question. So I just namely free loops is like direct product of M and omega, right?
Why?
Well, very naively, a loop is the same as a free loop is the same as a base loop plus a base point.
Yeah, but why is it a trivial vibration?
It's not obviously it's not a rigorous state.
Yeah, and this is why I ask a question, because it's
Okay.
it seems like that at the level of spectra there is splitting like this. I mean, suspension of direct product, infinite suspension of direct product of ordinary spaces is sum of infinite suspensions, right?
Mm-hmm.
It's reasonable to ask if a fiber of rho or phi, how we call it,
Rho.
is m minus Tm.
Yeah, so I understand the question, but I don't have any answer to it. I'm sorry.
Oh, the answer is we don't know.
Yes.
Well, it's a good question, but the answer is we don't know. And conversely, it makes sense to ask whether the second arrow, the one in number 3, that doesn't have a section.
So this arrow.
Yeah, the one on the bottom.
Oh,
Yeah.
once again, I don't know.
Well, again, it's not immediately clear.
Yeah, if it had a section, then maybe the answer to Sasha's question would be yes, but we don't even know why this suspension spectrum splits off from this not based loop spectrum, unbased.
Well, maybe if we compute some examples later on, we'll see whether or not these guesses are realistic. At the moment, we don't have any examples, and says I'll make what's happening.
By the way, I think that my suggestion is so what happens in I want to estimate size of say ordinary homology of left side, which is homology of groups, and homology of right side is not a homology. No, it's reasonable. Okay.
So it would be nice to understand how this CS how this homology ring of free loops looks like, for example, I don't know, for two sphere.
For two sphere,
I mean, we know how the base loops homology looks like.
there is computation
I'm sure.
of it will sound surprising of Fagan because it's related to for free sphere. For free sphere, it's related to homology of formal vector fields, and the answer it is
Really?
yes, and the answer is
Then I understand why it's
uh,
Fagan's interest.
The homology of free loops is generated by homology of base loops, which we know is generated by one variable in degree 2, and there is pullback of three-dimensional homology from sphere, so this just tensor product.
Okay. Then probably homology does not look reasonable.
Essentially, what we're talking about, we're talking about free loops, base loops on spheres.
On S3. Right. The homology is just tensor product, is just free algebra on generator in degree 2 and degree 3. Say over Q.
Yes, well, this is a good example. I think, well, we have a spectral sequence. Free loops go by evaluation to M, and the fiber is omega. And I don't think, well, this is a fiber bundle, so we have a spectral sequence. I don't think it always fits. I've forgotten, the problem splits for M equal some spheres, but not some other spheres. I've forgotten the answer. And by the way, well, it's.
The statement that fiber of this map is have size of M is not. There's no contradiction to statement that spectral sequence doesn't.
I think we consider different spectral sequence. We consider spectral sequence of bundle from LM to M with fiber omega M, not the bundle from LM to omega M with fiber M. I'm not sure that there is even such a bundle.
Anyway, well, another question is we've been talking about loops and free loops and so on, and well, presumably the reason was we started with the Kelvin bracket and then this sort of involves loops at the beginning. But an interesting question would be to see whether this